All right, so for the first lecture of 124-104, we will talk about measurements and mostly covering the basic skills that we will be using in this course. This first lecture will also be helpful for the first lab tomorrow because we will cover some stuff about dimension, unit conversions, and scientific notation. We will talk about uncertainty and confidence interval. So you will do a lot of uncertainty calculations in the labs when you do a lot of measurements. And for every measurement, you should account for uncertainties in the measuring device or the measuring technique, for example. So we'll cover some about uncertainty in this first lecture, as well as presenting your answers appropriately using the correct number of significant figures. Right, so in physics, we measure a lot of things, and that's why your lab is a very practical component because you will be doing experiments and you will be measuring quantities. All right, so when we say measurement or when we measure, what we're essentially doing is we're using a tool to compare a physical quantity to a standard. Okay, right? So if, for example, you're measuring your weight, then the physical quantity you're measuring will be your mass, and you are comparing that to some standard. We will define physical quantity and standard one by one, right? Physical quantity, it's essentially just a number that results from the measurement that you've made to describe a properties material. For example, you measured the length of a book and the ruler gave you a number of 10 centimeters, right? So 10, which is the number, is the magnitude or how long the book that you measured is. And then centimeters is what we call units. The unit is what tells you, the unit of your measurement tells you the standard for which you are comparing the number that you've got from the ruler's measurement. So when we say physical quantity, it consists of two things. Firstly, the number, which gives you the magnitude or the size of the thing, of the object that you measured, plus the unit, which gives you some sort of standard. So measuring the length of the book gives you 10 centimeters. 10 is the magnitude or the number, centimeters is the unit or the standard. As you can imagine, without putting the correct unit, the physical quantity doesn't have a meaning, because if you just say that the book is 10, you don't know whether that's 10 centimeters or 10 kilograms or 10 stacks of books, right? If you just give a number without the unit, the physical quantity becomes useless. And therefore, in every measurement that you make sure that you include the units together with the number that you've measured. Okay, the unit that you use depends on the dimension that you are measuring or you are considering. In this course, you will encounter these three common dimensions: the dimension of time, length, and mass. Electric charge, we will not really cover electricity in this course, but I just put it here just to show that electric charge, or it is it's an example of a dimension. And when you compare quantities, you are essentially comparing quantities with the same dimension. So for example, a day is shorter than a year, you are comparing the dimension of time. So dimensions are given here. length, mass, and time. We will encounter that. I think we will also do some thermodynamics in this course. So you will also encounter the dimension of temperature. These dimensions are also called base quantities. And for each base quantity, there is a corresponding unit, the standard for which we compare our measurement. This table summarizes the unit that corresponds to each of the dimensions, as well as the symbols that we use for each of the units. Right. So for example, you're measuring the length of the book. The physical quantity will be the number you measured, say 10, plus the unit centimeters or meters. Okay, that will give you a physical quantity of 10 centimeters for the length of the book. And sometimes you combine units and combine measurements, in which case we have what we call derived units, which is essentially just combining two or more of these base quantities. Area is an example of a derived unit. You're combining two lengths, and therefore the unit will also be a combination of each of the units of those dimensions, and hence you have meter squared for the unit of area. Velocity and speed is also a derived unit. We will talk about velocity and speed in the next lecture, but essentially you're combining two dimensions, length and time. You're combining the base quantity or dimension of length with the base quantity or dimension of time. And for the unit, you're essentially also just combining the units of each of the base quantities. And therefore, the unit for velocity is called a derived unit, meter per second. Right? Sometimes you will be dealing with very large and very small numbers. In physics or in sciences in general, you will encounter very large and very small numbers. And to deal with these very large and very small numbers, we use what we call unit prefixes. Okay? This table here summarizes some common unit prefixes. I think we will be using mostly, I guess, until these unit prefixes will be very commonly encountered in this course. Okay, they are just prefixes that we use as shortcuts to abbreviate multiples of 10 in the SI system or in the scientific notation. So the prefix is added to the base unit, right? In the previous slide, we saw that meter is the base unit for the dimension of length. Okay, kilo is the prefix that you add to the base meter, and hence you have the unit kilometer abbreviated as km. Because kilo is abbreviated as K, and meter is abbreviated as M. So 1 kilometer essentially means 1 times 10 to the 3. Times 10 comes from the prefix kilo or K. Okay, another example is millisecond. The prefix here is milli. The base unit is second, which is the base unit for the dimension of time, right? So we write that, we abbreviate millisecond as ms. If you look at the table of prefixes here, milli has an abbreviation of m, right? Seconds, of course, is abbreviated as s. And if we write down milliseconds as a number, we have 1 times 10 to the minus 3. Because again, looking at your prefix table, milli is equivalent to 10 to the negative 3 or 10 to the minus 3. Hence, 1 millisecond is 1 times 10 to the minus 3 of a second. right? Okay, just a quick note and a quick revision. A negative exponent is equivalent to that number being in the denominator. So 10 to the negative 1 is the same as 1 over 10. And we can apply that to units as well. So seconds to the minus 1 is the same as saying it's 1 over second. All right, so we've done base units, physical quantities and prefixes. Now, as I've mentioned, you will be dealing sometimes with very large and very small numbers. For example, here the mass of the sun is given by this number. I'm not going to read every digit because it's a very, very big number. It has so many digits, especially it has many zeros. Okay, or the mass of the electron is this number here. It's less than 1, 0 point something something. So it's a very small number. So when we're dealing with very large and very small numbers, instead of writing the whole number with all the digits like this, we use what we call scientific notation. Okay? So in scientific notation, we are putting a number into a specific form, which is shown here. It's a times 10 to the b. A is a number between 1 to 9. Okay? And B is what we call the power. The power can either be positive or negative, depending on whether our number is very, very big, like the mass of the sun, or whether the number is very, very small, like the mass of an electron. Right? So just as an example, let's look at the mass of the sun. As I said, it's a very, very big number. So to put this very big number in scientific notation, you need to find A. A should be a number between 1 to 9. Okay. If you have this number, it's sort of an unwritten rule that the decimal place is at the end of the last zero here. All you have to do is to move the decimal place so that you come up with a number that's between 1 to 9. So you can move it 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Okay, so if you move the decimal place 30 spaces to the left, you arrive with 1.989 and then all the zeros, but essentially you arrive at a number that's between 1 to 9. And that enables you to find what A is. So A in this case is 1.989. And B is the number of spaces that you had to move the decimal place to in order to get A. So you move the decimal place 30 spaces to the left, and hence you have B equal to 30. Okay. You can see here that if the number you're writing in scientific notation is very big, it's more than 1, then the power of B is positive. While on the other hand, let's look at a very, very small number, the mass of an electron. You have 0 point something. So that means you are dealing with a number less than 1. Again, similar procedure to write this in scientific notation. You need to move the decimal place so that you arrive at a number between 1 to 9. So you'll have to move the decimal place to the right, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and then one more 31. Okay. Right? So you really have to count the number of spaces that you move this decimal place. It's how everyone does it, right? So you have 9.1 and all of these. numbers here, it's a number that gives you A, and then B is the number of places that you moved the decimal place to in order to arrive at A. Since you moved 31 spaces, B will be 31. Okay, it's a very, very small number, and hence that's a negative power there, negative 31. All right, any questions so far? Or very good. I don't see any questions in the chat box, so I guess we can proceed. Yeah, so scientific notation allows us to write very big and very small numbers into a more compact form. It also has the second advantage that it allows us to explicitly specify the number of significant figures. Okay? Um, so we will talk about significant figures later on. How do we determine the number of significant figures? And then how do we use the scientific notation to deal with significant figures? But before we go to significant figures, another skill that you will need a lot in this course will be converting of units. Okay, we will often deal with dimensions with given in different units. For example, you're given the dimension of length in centimeters, and you want to convert that to the base unit of meter in order to combine different dimensions consistently. So we should be able to convert units between convert units between different standards that are given to us. So here, let's use money to begin and understand conversion of units. Hopefully it's something that everyone can understand, conversion of money. Say we wanted to convert New Zealand dollars to British pounds. The most important thing that we need in order to allow us to convert is what we call the conversion factor, right? All right, so here, these ones are called the conversion factors. The conversion factor essentially relates the two units that we're dealing with, right? So we want to convert New Zealand dollars to British pounds. So we need to know how many New Zealand dollars are there in a British pound, or we need to know how many pounds are there in a New Zealand dollar. Okay, so the conversion factor is necessary for us to be able to convert one quantity into another. Say, for example, we want to convert 500 New Zealand dollars. How many or how much British pounds do we have in 500 New Zealand dollars? I have, well, there are several ways of doing unit conversions, and maybe you've encountered one method in school, or if you do a Google or YouTube search, you will see several methods of doing unit conversions. Some phones can convert money, but in this course, you have to know how to convert units manually, right? I use this method. Okay, so the method I'm presenting here is what I feel is the simplest. But if you have learned a different method, of course, you're welcome to use that method as long as it gives you the correct answer. So the method I use is, first, I break the quantity into number and units, right? The physical quantity consists of a number and a unit. So $500 consists of 500 pieces of $1. Okay. The reason why I break the quantity into the number and the units is then it allows me to easily change what I don't want, easily change the unit I don't want to the unit I want using the conversion factor, right? So I don't want dollars, I want pounds. And in order to convert dollars to pounds, I use the conversion factor that relates the dollar to the pound. So once I replace the unit with the conversion factor, I then carry out the calculation. 500 times 0.5 is 250, and then just use the new unit that came from the conversion factor. Right, so let's look at an example that is, more related to a dimension that we will encounter often in physics, the dimension of length. So we want to convert 40 inches to centimeters, meaning how many centimeters are there in 40 inches. We have this conversion factor, 1 inch equals 2.54 centimeters, right? Okay, so I break down the physical quantity. The physical quantity is 40 inches. I break it down into the number and the unit, right? And then I change the unit that I don't want. I don't want inch. I change that to the unit I want using the conversion factor, right? And hence, I then do the calculation 40 times 2.54 with the new unit that I want, and I arrive with 101.6 centimeters being equal to 40 inches. Good. Any questions about unit conversion? All right, so if no questions, let's try something a bit more complex. And I'll give you like maybe 1 or 2 minutes, a few minutes to try and figure this out. And then we will look at the solution. So convert the area, 25 millimeters squared or square millimeters, into meters squared or square meters. Okay, how do you convert millimeters squared to meters squared? I've already written down the conversion factors here, which you can also see from the prefix table, because milli is a prefix, right? 10 to the minus 3 is what milli is equivalent to. So I've written down the conversion factors here, and just try to convert this before we look at the solution. Okay, right, so if we do the method I've just presented, you break down the physical quantity into the number and the units. Okay, just the tricky bit here is to remember that if you have a square, like millimeter square, that means millimeters times millimeters, right? So millimeter squared, I've written down as 1 millimeter times 1 millimeter. Okay. If it's, of course, if it's millimeter cube, then that means millimeter times millimeter times millimeter, right? But by writing it down millimeter squared as millimeter times millimeter, you can clearly see that you need to convert millimeters to meters 2 times, right? You have to convert 1 millimeter to meters, and then you have to convert this other 1 millimeter to meters. Okay? How do you convert millimeters to meters? You use the conversion factor that relates millimeters, the unit you don't want, to meters, which is the unit that you want. Right? So, right, that's their conversion factor there. You simply replace 1 millimeter with the meter equivalent, but you have to do that 2 times. Right? Then you carry out the calculation and you end up with meter squared as your unit because you have their meters 2 times. Right? So here is some practice for writing in scientific notation as well. Good. Cool. No questions in the chat box. So let's move on to significant figures. Right. So significant figures, this is the definition of significant figures. But the more important thing is, how do we determine how many significant figures are there in a number? There are some rules that tells us how to determine the number of digits that can be reliably known. All non-zero digits are significant. So 6.43, they're all integers, they're all non-zero, so you have 3 significant figures. If the 0 appears between 2 non-zero digits, like these 2 zeros here, they are significant, meaning they're important. Zeros after a decimal point, they are significant as well. Okay. Here's an example here. But zeros before, leading zeros, so zeros before decimal place and before non-zero, before an integer, like these 3 zeros here, they are not significant. Yeah. This 0 is significant. We count it as significant because it's between 2 non-zero numbers. This 0 after 2 is also significant according to this third rule here. Right? The ambiguous rule is, how do we deal with zeros that do not contain a decimal point? So say here, this 64,000 meters, do we count it as 2 significant figures or 5 significant figures? In this course, we usually count this as 2 significant figures. In the test, we will usually explicitly say 64,000 and then put like a parenthesis or a bracket and say 2 significant figures. So that makes it clear that we're only dealing with 2 significant figures. All right. But if we really want to remove the ambiguity, we write the number in scientific notation. So if we write the number 64,000 in scientific notation, that will be 6.4 times 10 to the 4 because the decimal point is here, and you move it 1, 2, 3, 4 spaces to the left in order to have 6.4, a number between 1 and 9. And the power is 4 because you moved the decimal place to the left, in which case it's now clear that you have 2 significant figures. Right? If we want 3 significant figures, then we add a 0 after the decimal point and after 4, and hence we clearly see it has 3 significant figures. But then again, in the test, as I said, we will specify how many significant figures we want you to consider in order to remove the ambiguity. Okay. It's usually when we add or subtract. Well, maybe the question is, why is it important to know number of significant figures? It's important to know because sometimes you're performing a calculation and your calculator gives you lots of numbers, say 2.56970825, like lots of decimal places, lots of numbers after the decimal point. How do you know when to round your answer, right? Um, and this is where significant figures come in. When you're adding or subtracting numbers, then you round your answer to follow the least number of significant figures. Okay? And an example is given here. And when you're multiplying or dividing, we also follow the least number of significant figures. Okay? Um, so that's why significant figures are relevant, and I've discussed them because online you'll do your assignments online on Stream, and sometimes Stream is a little bit picky with rounding. So we follow the rules of significant figures in order for you to know how to round your answers that you will put on Stream. Um, in order for Stream to accept the answer that you've entered. Okay. Just remember that when you're doing multiple calculations, keep all digits while you're doing the calculations and only round off at the end when you're putting in your final answer. And otherwise, you'll have rounding errors and maybe you'll be too far off from the tolerance that we have set on Stream. Good. And just a quick note, say, for example, you're doing your online assignments and you enter your answer and you find that Stream rejects your answer and you're pretty confident that your answer is correct. Please do let me know, send me an email because I can look at your answers. And if it's a rounding error that's only a few numbers off from what Stream expects, then I will award you the point. So there's, I mean, significant figures, we will follow them, but they will not be strictly enforced as such. What's more important is for you to know how to work out problems. So if you encounter any problems on significant figures during the Stream assignments, then please do contact me and I'll deal with that fairly. Right. Okay, so for the rest of the time, we will talk about something that you will encounter in the lab. I will not discuss measurement and uncertainty to as much detail as I did for the previous slides because you will do measurement and uncertainty in the first lab, and that will be the best place to actually practice measurement and uncertainty. The key point is that whenever you measure a quantity, there will always be some kind of uncertainty because no measurement is really exact. Okay? Here is a picture that demonstrates this concept. When you measure the length of or the width of this plank of wood, okay, sometimes the edge of the wood falls between two discrete lines in the ruler. And in which case you sort of need to estimate what is the actual width of this wood. And that's where the uncertainty comes in. The measurement that you write down is not really exact because you're sort of estimating what's the number between the two lines in your ruler. Okay? So to indicate the uncertainty or the unexactness of your measurements, we use this sort of plus and minus notation to let us know that, okay, we estimated the measurement a little bit. Okay. 0.1 centimeters comes from the smallest accurate measurement that your tool or measuring device can accurately measure. Well, a simple explanation of that is the ruler. One small division in your ruler is 1 millimeter or 0.1 centimeter. Hence, you use that as your uncertainty, plus minus 1 millimeter or 0.1 centimeter, because you can accurately measure the length to 1 millimeter, which is one of the smallest divisions in your ruler, right? Right. So to account for the estimation that you did in your measurement, you then have to write the number that you've measured, the estimation that you did, say 8.8, plus and minus the uncertainty in your measuring device. 0.1 centimeters in this case, which, as I've mentioned, is the smallest scale division in your ruler. Okay. Right? So here's another example. If you're measuring the mass and the scale only measures up to 0.05 kilograms, meaning the smallest division of your scale is 0.05 kilograms. You then use that as the uncertainty in your measurement, plus minus 0.05. 67.2 is whatever measurement you get, but you also put the uncertainty in that measurement because your scale is essentially estimating that your mass is between 67.16 kilograms to 67.24 kilograms. 67.16, of course, came from 67.20, take away 0.05, and 67.24. This should be 25. Then in this case, this should be 0.4 for that to be correct. 67.24, of course, came from 67 plus 0.04, the uncertainty in the measurement. Right? Okay, so I'll skip this sources of uncertainty. You can read this slide. It's essentially uncertainty or estimation comes from either the measuring equipment, the system, or statistical errors for when when you measure the length multiple times, you're estimating your measurement multiple times, so that gives you random or statistical errors. Okay, right? So because you're estimating, uncertainty always requires judgment. But we have some steps or some rules that we often follow when we're estimating uncertainty. You will do this essentially in the first lab. You will practice these first 4 steps. But what I want to emphasize is these last 2. How do we round our answers? Keep the rule we will use is that you keep only one significant figure for the uncertainty and adjust your measurement to the same precision or same decimal place. Okay. So to illustrate that, here's an example. If you measure the weight of an object 5 times, you take the average of the measurements, which gave you this 67.251 kilograms with an uncertainty of 0.021 kilograms. How do you correctly round these numbers and present your final answer? First, start with the uncertainty, 0.021 kilograms. You have to round that to one significant figure, hence you have 0.02. Since you have 2 decimal places, right, 2 decimal places, you then round your average or your mean to do 2 decimal places to follow the same precision or the same decimal place of your uncertainty. Right? Cool. Right. When you combine uncertainties, we again follow these two steps, which I will not discuss so much in detail because in the lab you will learn this. But we first get a central or the best value and then the biggest possible value. And then we subtract these two using a method called the brute force method. So say, for example, you measured the length, the width, and the depth of a book. Each measurement, of course, has its own uncertainty. Okay? When you calculate the volume, you're multiplying the length, width, and depth. To get the best estimate, the mean value of the volume, notice how you're multiplying the length, the width, and the depth, ignoring the uncertainties, right? So first, ignore the uncertainties and just calculate the volume of the book using your measurements. Okay? You arrive with this volume here. And then get the biggest possible volume that the book can have, right? Since you are multiplying, you need to multiply big numbers, and that's where the uncertainties come in. Okay? So 26.1 becomes 26.2 because you are adding the uncertainty to the measurement. 21.1 comes from adding 0.3 to 20.8, and 2.4 comes from adding 0.05 to 2.35, right? So you have the biggest possible length, width, and depth. You multiply them and you get the biggest possible value in volume. The uncertainty is then the biggest value you've calculated minus the best value. That gives you 51 centimeters. Round that to one significant figure, 50. Right? And then, so you have plus minus 50 as your uncertainty, one significant figure, and the actual volume of the book will come from the central or the mean value that you've calculated, disregarding the uncertainties, but remember to round your number to the same precision as your uncertainty. So your uncertainty is 50, it's in the tens precision, so your measurement should also be rounded to the nearest tens. 1275 rounded to 1280. And you'll have more exercises and practice in the lab tomorrow on brute force method, as well as accuracy and precision. So I'll leave you with, yeah, that's the end of our lecture anyway, but I leave you with the slides on stream, as well as the video recording. And I guess I'll see you in the next lecture tomorrow. I'll see you online in the next lecture. Unless you have any questions, feel free to stay and ask me or type in the chat box. Otherwise, I'll end the lecture here and I'll see you tomorrow.